when we talk about um, when we talk about, there we go. So we're recording good. Yeah, what was I saying? When we talk about pKa units. So keep your eyes peeled for that. All right, so chapter 3, we're dealing with acids and bases. If you go back to General Chemistry 1, you would have first learned about Arrhenius, acids and bases. And when it came to Arrhenius, an acid was something that donated H plus or formed H plus in solution, and a base was something that formed hydroxide in solution. That was the first definition of an acid and a base, Arrhenius. We're not actually going to look at Arrhenius definition in this chapter. We're going to look at Bronsted-Lowry, though, quite a bit. So Bronsted-Lowry, which I usually will just refer to as Bronsted. I'll usually leave Lowry out of it. And what they did is they broadened the definition of an acid and a base, and they said that an acid is a proton donor, and a base is a proton acceptor. Okay, and there's a whole reason why they had to broaden the definition. I'm not going to go into it right now, but it's something that's mentioned in the textbook, so you can take a look at that. And the last one is the Lewis acid base, which broadens the definition even more. And in Lewis acid base theory, an acid is an electron acceptor, and a base is an electron donor. And the way that my students remember this, I think, is acid acceptor. So it's two vowels. And if you have a base, it's an electron donor. So it's two consonants. It's a good way to remember that. Anyhow, so let's move into the first slide and let's talk a little bit more detail about Bronsted-Lowry acids and bases. You have to know the definition. You're going to see this about 10 million times, and I say that almost without hyperbole. The acids donate a proton and bases accept a proton. Okay, that's our definition in organic or in chemistry for the Bronsted-Lowry definition of an acid and a base. So here's a classic example from your good old Gen Chem 1 days. If you take HCl, which is a strong acid, it's a proton donor, and it can react with water. Water is not a strong base, but it can behave as a base. You might remember that water is what we call amphoteric. It can behave as an acid or a base depending on the situation. So we have our acid, which is going to donate a proton to our base. We end up forming the chloride ion, which is the conjugate base, and then we end up forming the hydronium ion, which is the conjugate acid. You've got to remember the name of the H3O plus ion, which is hydronium. And you've got to be able to draw the Lewis structure because we're going to see it a million times in here. So you've got to be able to identify acids, bases, conjugate acids, and conjugate bases. And I always ask a couple of questions about those on the quiz in chapter 3. So let's move on from there. It says a conjugate acid. If you're wondering, how do I identify the conjugate acid? Well, it's what you get when the base accepts a proton, and the conjugate base is what you end up with when the acid gives up a proton. If you're confused by this definition or these definitions right here, what we could do is we could just take a step back here. Think about the reaction in reverse. If you were to go in reverse, just think about the reaction backwards. Who's donating a proton? Well, it's clear that the hydronium is donating this proton and it's not here anymore. So that means the hydronium must be the conjugate acid, right? Because it was donating a proton in the reverse direction. And the chloride is accepting a proton to become HCl. A base is a proton acceptor, and therefore this must be the conjugate base. So to repeat myself, if you ever get nervous or unsure as to whether you're identifying the conjugate acid and the conjugate base correctly, you can always just think about the reaction in reverse and then remember the definition. An acid donates a proton and a base accepts a proton. All right, so if we go back to that definitions and we look at this reaction here, we see that we have an equilibrium. We have what we call the tert-butoxide ion is reacting with water. Then we end up with an alcohol. This is called tert-butanol. And you know this, of course. This is the hydroxide ion. So I'm going to label these. I'm just going to call this one, I'll use my blue pen. I'll call this one, go back here. I'll call this one 1, 2, 3, and 4. So if I look at number 1 and number 2, could anybody tell me which one of these, excuse me, is behaving as an acid, a Bronsted acid? Which one is donating a proton? Would it be the alkoxide or would it be the water molecule? Yeah, absolutely. It's the water molecule. Perfect. So this is our acid. I'll scribble that down here, right? Because it's a proton donor, right? It's giving up that proton in red. And the butoxide, this is our base, right? Because it's an H plus acceptor. Acceptor. So if I look at 3 and 4, could anybody tell me which one of these is the conjugate base? Which one's the conjugate base? Would it be 3 or 4? Yeah, thanks, Sarah. Absolutely. This is our conjugate base, and this is our conjugate acid. And if we just use the definition that's shown on the screen here, the conjugate acid is what you get when the base accepts a proton, right? So that's this here. And the conjugate base is what you get after the acid donates or gives up a proton. So that satisfies this definition as well. Give me a thumbs up if you follow me on acid, base, conjugate acid, and conjugate base, because now we're going to spice things up a little bit, and we're going to get into curved arrow notation in representing a reaction. All right, cool. That's great. Well, let's move on to section 3.2, which deals with curved arrows in what? Reactions. In chapter 2, we didn't look at any reactions. Chapter 2 dealt with resonance, which is something completely different, right? That just shows the delocalization of electrons around the resonance hybrid. In this section, we're going to actually show the electrons that are moving when we do an actual physical process. We're going to do a chemical reaction here. So take a look at this reaction. So we're using B minus here. We're using this for some kind of generic base. It could be hydroxide. It doesn't matter. It's neither here nor there. And then we're using HA to represent some kind of generic acid. Well, what you see is that you have the base grabbing a proton from the acid, right? The base is the proton acceptor. The acid is the proton donor. Therefore, this must be our conjugate acid, and this must be our conjugate base. So if you remember from chapter 2, whenever we show a curved arrow that has a double head on it like this, that represents the flow of 2 electrons. This arrow represents the flow of 2 electrons, and this arrow represents the flow of 2 electrons. And hopefully you remember that in a bond, we have 2 electrons, whether it's a sigma bond or a pi bond. No pi bonds to worry about here. But if you look at this first curved arrow that I'm highlighting in yellow right now, what that represents is the flow of electrons from the base as it grabs the proton, or it accepts the proton, because a base is a proton acceptor. Now, so that pair of electrons is going to form a bond. So this is a bond being formed. Now, there's no way that hydrogen can have 2 bonds. It's impossible. It can only have 1 bond. And therefore, this bond is going to have to break. So what do we do with that pair of electrons? Well, you see that the head of the arrow is ending up on atom A, all right? And so we see that it ends up as a pair of electrons, a lone pair on A, and then of course we give it a negative charge because we're gaining electrons there. So it says here that these are the same curved arrows that we used in resonance, but now, again, I gotta stress this, we're actually showing the physical movement of electrons, and learning how to draw mechanisms is one of the most valuable skills in this class. So what you're going to see moving forward in our textbook and in my lectures is that usually when I look at a reaction, I'm going to show you a mechanism for it. And if there is, God forbid, a mechanism that you don't need to know, I will tell you. And there's a few of them in the book that you don't need to know. But let me just put this bug in your ear right now, because I have not a bunch, but I have a few students who are interested in, things like med school and stuff like that, which I think is wonderful to have a goal in mind. And when it comes to mechanisms, if you think about, the quizzes that I give that are multiple choice, or the MCAT, which is a multiple choice exam, you might think, well, I don't have to draw anything on there. So as long as I can identify it, I'll be okay. I'm going to tell you right now that you won't be okay. No, you won't be able to identify it unless you can draw it. And so if I can really encourage you, you need to practice using a pencil and paper, and learning how to draw mechanisms is imperative. There's no way to escape or to get out of organic chemistry without drawing mechanisms. And it says here, it's one of the most valuable skills you'll learn in this class, right? Not only do we learn reactions in organic chemistry, but we understand the how and the why. All right, we understand why the electrons flow the way they do when we break bonds and form bonds. So let's take a look at a very specific example here. This is the hydroxide ion. If you remember this from your Gen Chem 2 days, because you would have seen it 1,000 times in there. This is hydroxide. This is acetic acid. It's a carboxylic acid. I asked you to memorize the carboxylic acid functional group. Just so you're aware, an organic acid like a carboxylic acid, it's not a strong acid. It's still a proton donor, but it's not a strong acid. It's a weak acid. So this one is acetic acid. This is the acid you would find in vinegar. And then we have the conjugate acid and the conjugate base. So what do we say here? We say that the hydroxide is a base, so it's a proton acceptor. It's going to accept the proton from the proton donor, and the proton donor is the acid. And so we're going to draw a curved arrow from a lone pair on the base, right? Because you need 2 electrons to form a bond, and we grab the proton. Remember, a proton is H+, right? We grab that proton, and the proton has no electrons, so you need to get both of the electrons from the base. So that's our bond being formed, the one I have highlighted in yellow. Now again, hydrogen cannot have 2 bonds, that's impossible. And so we break a bond, the bond between the hydrogen and the oxygen. Notice that the tail starts on the bond itself, what I'm highlighting in blue, and the head of the arrow ends up on the nucleus or on the oxygen atom itself to show you that that's where the lone pair is going. So some of the vernacular that we use, and I'll use this throughout my lectures, is we say that the base attacks the acid. Okay, sometimes you heard me say it grabs the proton, but sometimes we say it attacks. Attacks the acid, using a pair of electrons. And again, the acid cannot lose its proton without the base taking it. All acid-base reactions occur in one step. So meaning both curved arrows are drawn simultaneously. We have to draw both of them at the same time. You can't draw one being formed and then one being made, because then the hydrogen would exceed its duet of electrons, because it only has the 1s orbital available to it. Now, even if you're looking at this and going, oh Lord, this looks complicated. Well, first of all, it's not easy, number one. But number two, how are you going to figure it out? You're going to practice it over and over and over. So let's take a look at an example. It says here, all of the following acid-base reactions are reactions that we are going to study in greater detail later on in the class. For each one, draw a mechanism and then clearly label the acid base, conjugate acid, and conjugate base. I think the first thing we should do is draw in some lone pairs, because there's a whole holy host of them missing in here. First of all, on this compound, remember, when oxygen has no charge, it has 2 bonds and 2 lone pairs. Hydroxide is going to have 3 lone pairs on the oxygen. If I go over to an alkoxide, an oxygen with a negative charge has 1 bond and 3 lone pairs. And then finally on water, well, you know that one by heart. All right, oxygen has 2 bonds and 2 lone pairs. There we go. So if I label this, we'll do it like this: 1, 2, 3, and 4. Could anybody identify the acid here? Is it 1 or 2? Which one is the acid in this reaction? The proton donor. Absolutely. Yes, this is our acid. Thank you. And if this is our acid, this must be our base. Could anybody identify the conjugate base? Is it 3 or 4? Yeah, great. Sorry if you can hear that in the background. My son is like overly excited about his grandparents visiting. So this is the conjugate base, and this is the conjugate acid. Great. There we go. So conjugate base and conjugate acid. Now what we want to do is draw some curved arrows. So where the base is going to attack the acid, isn't it? All right, or it's going to grab the proton, because a base is a proton acceptor. So we're going to start with the tail of our arrow on a lone pair, and we're going to draw the tip of the arrow, or the head of the arrow is touching or grabbing or attacking the proton, right? But that would mean that the hydrogen would have 2 bonds if we left it like this. So we're going to have to take the pair of electrons in the bond between the oxygen and the hydrogen, so this pair of electrons, and we're going to move them onto the oxygen atom like this, and that is going to give us our 3rd lone pair over here. And that's the whole thing. That's the entire mechanism, just like that. Now, I don't have any other examples, so I'm going to switch over to a blank document because I want to try a couple more with you. just bear with me. Let's take a look at something like this. So these are just other problems from the book, but I thought it'd be good practice on a Monday. There's nothing you want to do more than practice some organic chemistry mechanisms. So this one, so we have a ketone plus hydronium, and that's going to be in equilibrium with this thing. We call this an oxonium ion. We're going to see this in a little bit today. And then, of course, you would end up with water here. So I'm going to call this 1, 2, 3, and 4. And while you're thinking about that one, I'm going to write another practice problem here down at the bottom of the screen. So hopefully you're following along with a pencil and paper, right? Very carefully. So this one's kind of similar to one we looked at earlier. But anyhow, we'll take a look. All right, I'm going to call this 5, 6, 7, 8. All right. So if I look at, and again, I know you know the answer. I just want to practice it with you one more time. If I look at 1 and 2, could anybody tell me which one is the acid? I'm missing a formal charge here. Which one is the acid? Would it be 1 or 2? Which one is donating the proton? Yeah. Thanks, Sean. Thanks, Kiana. Perfect. And so the base, which is going to be the ketone, is going to grab a proton. Remember, it doesn't matter which one you take. You can pull this one off. That doesn't matter. Okay, we're just going to grab this one here. And then remember that hydrogen can't have 2 bonds. So we're going to have to break this bond and put a pair of electrons onto the water molecule. And that's why the water has 2 lone pairs. There we go. And again, I told you that this species here, this is called an oxonium. An oxonium ion is what it's called. Anyhow, I'm going to erase that and just make sure that we all understand that this is our base, this is our acid, this is our conjugate acid, and this is our conjugate base. All right, let's try the one on the bottom. Which one would be the base? Would it be 5 or 6? I think this is the last time I'll ask you this, then we'll just move on and assume you're good. Yes, absolutely. You guys are so fast. So I end up grabbing the proton from the carboxylic acid. I put a pair of electrons on this oxygen. There we go. So this is my acid. This is my base. This is my conjugate base. And this is my conjugate acid. And there you have it. Give me a thumbs up if you're following me even like 60% of the way on this. The reason I don't say 100% is because you'd have to practice it to master. I don't see how you could master it without practicing it. Pretty much impossible, in my opinion. All right, so let's go back here to our slides. All righty. So we were somewhere around here. And now we're going to get into quantifying acidity. So we're going to look at 2 ways to evaluate acidity or basicity. One way is that we're actually going to use numbers. So that's what it means by quantifying. And I know you know that. But first thing we're going to do is look at numbers. You can never argue with numbers, really, or it's very difficult to do that. And then later on, I'm going to teach you a way to just look at the atoms that the protons are attached to. And it'll make more sense when we get there. But you can evaluate kind of a relative acidity doing that. But let me tell you right now, if you can memorize what we call pKa values, so that's what we're going to largely focus on in this section, or pKa values. If you can memorize a bunch of those, I'm telling you, they will always be useful. You will never regret memorizing them. And there's some that you have to memorize, and I'll show you exactly which ones those are. So let's go back to our Gen Chem 2 days. If you remember, you would have done an entire chapter on equilibria. It says quantitative strength analysis using numerical data. We use numbers to compare how strong an acid is. So if you remember Ka, so this would be Gen Chem 2 if you're at UCCS. It would be chemistry 1411. It's the acid dissociation constant of an acid that's dissolved in water. It's the measure of the ability of an acid to donate a proton to water, or its ability to dissociate in water, really. So if we write a K equilibrium expression for this reaction, so we have an acid plus water, gives you a conjugate base plus hydronium. If you write out a K equilibrium expression for that, we get hydronium times the conjugate base divided by the acid multiplied by the concentration of water. We eliminate the concentration of water because it's constant, and I won't get into the concentration. But anyhow, we simplify the expression to Ka, which is the acid dissociation constant, which is the concentration of hydronium times the concentration of the conjugate base, so the products, right? Products divided by the concentration of the reactant, which is the acid. So if you think about it, the stronger the acid is, right? If this is our acid, the stronger it is, the more the equilibrium is going to lie to the side of the products, because what's the purpose of an acid? It's to donate a proton. So the greater the numerator is, the stronger the acid is going to be. So the bigger the Ka, the stronger the acid is. The weaker the acid is, the smaller the Ka is going to be. So if the acid is strong, is the Ka going to be bigger than 1 or smaller than 1? Can anybody answer that? We have a big numerator when we have a strong acid because it dissociates so much. Yeah, it's going to be bigger than 1, right? So we'll circle this. It's going to be bigger than 1. All right. There we go. So let's move on from there. Now, it turns out the Ka values have a huge range. They can go all the way from 10 to the negative 50 to 10 to the power of 10. I don't know about you, but if I had to write out 10 to the negative 50, 0.00000, right? I'd be the first guy to lose track of my zeros. And so we have a way to simplify that, is that we take the negative log of the Ka and we use what are called pKa values. So instead of using 10 to the negative 50 to 10 to the power of 10, we use pKa is equal to the negative log of Ka, just like pH is equal to the negative log of the concentration of H+, okay? So pKa values can range from negative 10. So if you have 10 to the power of 10, you're going to get a pKa equal to negative 10, because remember, it's the negative log of the Ka. And if you have a pKa of 10 to the negative 50, it's going to give you a pKa equal to 50. So what does that mean? The greater the Ka, the stronger the acid. So if you have a low pKa, that means you've got a strong acid. So low, well, I guess it's written on here. Low pKa equals stronger acid. High pKa equals a weaker acid. So something like sulfuric acid, since that's an acid I know that everybody knows off by heart, H2SO4 has a pKa, I think, of around -9 or something like that. I could just look it up in the textbook. Yeah, it says -9 in my slide. So a really strong acid is a really low pKa. A really weak acid has a very high pKa. All right, so let's take a look at a table here. This is table 3.1 from the textbook. I'm going to actually not go over this table in detail with you because I have a better version of it in the next slides, but it says there are more acids and pKa values in 3.1. So it's not in the inside cover of your textbook since you have the electronic textbook, but what you want to use is table 3.1. Table 3.1 is going to be your kind of Bible of pKa values. It's the values that you will need to know for this class. So the way that they have them organized is here. So this is table 3.1 from your textbook, essentially. And there's only one thing I'm going to add to it, which doesn't even need to be added, but I'm just going to throw one thing at you. So let's go over them. The first one is sulfuric acid, right? It's a very strong acid, so it's going to have a very low pKa. It's a pKa of -9. You have to memorize all of these. So let me go back here. You want to, where's my table? There it is. You want to, I'll put it here, memorize all of these. Okay, they will be so helpful for you in this class because you can't argue with pKa values. So first we get sulfuric acid, -9, very strong acid. The next one I told you, this is called an oxonium ion. And you're missing a lone pair there, but it's also a very strong acid with a pKa of -7.3. Look, hydrochloric acid has a pKa of -7. So you see that hydrochloric acid is 100 times weaker acid than sulfuric acid. And if you're like, well, no, where did you get 100 from? Remember that every change in a log unit is a power of 10, right? So the difference between -9 and -7 is 2, which is the same thing as 10 to the power of 2. Right, which is equal to 100. So that means that sulfuric acid is 100 times a stronger acid than hydrochloric acid. Then we go to hydronium, the conjugate acid of water, which is negative 1.74. And anything that's below zero, so anything below zero, in chemistry 3101, I'm going to put here chem 3101, strong acids. Strong acids. We'll put here pKa. It's going to be less than zero. If you have a pK of 0 or less, we consider that to be a strong acid in this class. So now we're moving into weak acids. A carboxylic acid, is it an acid? Hell yeah. Does it donate protons? Absolutely. But is it a strong acid? No. Okay. It's not a strong acid. So it has a pK of about 4.75 or 5-ish. The next one, if you're wondering what the heck is this thing here, this is called what we call a 1,3 dicarbonyl. So if you count 1, 2, 3, we call this a 1,3 dicarbonyl. You can also call it a beta, what would you call it? A beta ketone is another way of describing it. Well, 1,3 carbonyl will suffice, and it has a pK of 9. I don't know what else to tell you other than memorize that number. The next one is phenol. So this is phenol is the name of this compound. My students, I think, have told me that OL, right, kind of looks like the number 10 backwards. So is equal to 10, and you can see it's got a pK of around 10. The next one, water. Well, there's a little blurb about water's pK in the textbook, but we're just going to take 15.7 as the gospel truth in this class, so we'll memorize that one. The next one you might find a little puzzling is we have two alcohols. We have ethanol and terbutanol. And if you look at the two here, what's the difference between 16 and 18? It's 2. So that would be the same thing as 10 to the power of 2, which is equal to 100. So that means that this is ethanol. Ethanol is 100 times more acidic than this alcohol, which is called terbutanol. We actually saw this today already. And you might be wondering, well, why is that? You know, they look pretty similar to me. Well, I'm going to explain it to you later on. The next one is acetone, but this is just a ketone. So ketone has a pK of about 19. Does anybody recognize this functional group in here? Can anybody identify this functional group for me? I know we're all pretty rock solid on our functional. Yeah, it's an alkyne. Thanks, Sarah. So this one is an alkyne. Alkyne. So if you have an sp hybridized carbon attached to a hydrogen, the pK is around 25. Could anybody name this molecule? Since we're naming molecules, could anybody name NH3? What's the name of NH3? I mean the actual name. Yeah, thanks, Sean. It's ammonia. Yeah. So Sean, I'm going to write here ammonia, or I'm going to put here an amine, any kind of amine that we're going to look at, or I should say primary or secondary amine, really. Let me scribble that down here. Primary or secondary amine. Okay, it has a pK of around 38, so now we're getting into really weak acids. The next one is when we have a bond between an sp2 hybridized carbon and a hydrogen. It's around 44, and then you get to the weakest of the acids. So this is an alkene, and this one is an alkane. An alkane is not a functional group, but this is an sp3 hybridized carbon, and this is the weakest of all the acids. So this thing doesn't want to donate a proton whatsoever. I'll add one thing on here, just because it shows up from time to time in the textbook, is if you have, that's pretty crummy drawing, if you have an aromatic ring, okay, the pK of the proton on an aromatic ring is about 43. So pKa is equal to 43. But if you're wondering, well, why didn't they put it in the table? Because it's a bond between an sp2 hybridized carbon and the hydrogen. And you can see here that they put 44 and 43, come on. It's a pretty small difference, so it's going to work. Also, another thing that you should remember from your good old Gen Chem 1 days, and if you don't, I'll refresh your memory right now, or you might have noticed just by looking at this table, is that the stronger an acid is, the weaker its conjugate base is, and that the weaker an acid is, the stronger its conjugate base is. Now, if you are just thinking, I'm going to memorize that and then I'll be good, that's fine. I suppose you could, but can I just take 1 second and explain it to you? Okay, if we look at a really strong acid, okay, like sulfuric acid, we're talking very strong acid. What's the Bronsted definition of an acid? Can anybody refresh my memory? What does an acid want to do? Exactly. It wants to donate protons. That's its job. It likes to donate protons. It wants to donate a proton more than anything else on this page. And so if it wants to donate a proton so bad, it tells you the evidence is there that if this thing wants to lose a proton so bad, it means that the conjugate base is actually going to be pretty stable. Once the acid, and I'm going to take on the persona of sulfuric acid, once the acid has lost its proton, the conjugate base that's left over is like, yeah, this isn't so bad. You know, I'm cool. You know, this guy is actually pretty comfortable the way it is, right? He's like, I lost a proton, but I'm okay because the acid that I come from is so strong, it wanted to lose a proton, so it's okay. So if you think about it, if the base is comfortable, if the base is stable, that means it's not going to try and grab a proton. It's not a strong base. It's going to be kind of like meh, indifferent towards protons. Okay? Whereas if we go to the opposite end of the spectrum, if you look at something like an alkane, so this molecule is called ethane, which is CH3, CH3. You see that this thing has a super high pKa. That means it is the weakest of the weakest acids. That means it has no desire to donate this proton whatsoever. It does not want to do it. So that means that if it does lose a proton, this molecule is kind of, or this ion is like, oh, where did my proton go? You know, it wants it back so bad that this is going to be a very strong base. And so again, the trend that we see is the stronger the acid, the weaker the conjugate base, the weaker the acid, the stronger the conjugate base. And if you're thinking, well, if I kind of memorize the strengths of the acids and their pKa's, you know, should I also have an idea about how base strength works? Absolutely, absolutely. And we're going to actually look at base stability quite a bit in a few minutes. Okay, so check it out. Quantifying basicity. It's right here. Anyhow, we're going to look at more of a qualitative treatment in just a second here. But again, this is me just putting it on a slide. You need to know that the stronger an acid is, the weaker its conjugate base is. Is everybody with me so far? Now that we've kind of covered pKa, any thumbs up on that one? Okay. All right, we're going to look at a couple of problems before we move on. We're going to try to identify some protons based on their pKa, and then we're going to look at some equilibria. Okay, so let's move on and let's take a look at this question here. So this is propranolol. I'm sure some of you have heard of this drug before. It's an antihypertensive, so it's used to treat, if you know anybody that's got high blood pressure, they might take this compound. It says use table 3.1 to identify the most acidic proton in the compound and identify or indicate the approximate expected pKa. You know what I'm going to do? I'm going to highlight a few protons. I'm going to put this one here. I'll put this one here. And I'm going to highlight this one in yellow. I'll highlight this one in red. Highlight this one in green. And I'll highlight this one in blue. Okay? So I'm just going to start with those protons. Could anybody tell me, out of these 4 protons that I have highlighted, which one of those would be the most acidic? And it's not a trick question or anything. If you go to the table, which one of these functional groups or which one of these protons do you think would have the lowest pKa? Yeah, all right. I like the way you're thinking, Sean. So Sean says probably the one on the oxygen. I think you're right, Sean. Let's take a look at all of them, okay? If we start with the one on an aromatic ring, we said that when you have a bond between an sp2 hybridized carbon and a proton, the pKa was around 43, 44. It doesn't even have to be exact, okay? Look, pKa, we'll put 43 to 44. So that means that any of these protons that I'm drawing right now, these are all between sp2 hybridized carbons and hydrogen. So every single one of these is going to have pretty much the same pKa. It might differ a little bit, but not too much. If we go to the one in red, what's the hybridization of the carbon that I'm highlighting in red, or that I put the red circle around? What's the hybridization of that carbon? The carbon I have the red circle on. What's its hybridization? Yeah, absolutely, Katana. It's sp3, isn't it? Right? So if we have an sp3 hybridized carbon, we said that the pKa of a proton that's attached to an sp3 hybridized carbon, let me just write here, sp3, and then I'll erase this here. We said the pKa was around 50. pKa is around 50. So that means that every single one of the protons there, here. Where's my red highlighter? Here, 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 here. Anything that's on an sp3 hybridized carbon, including this one as well, everything is going to have a pK of around 50. Then if we look at the one on the hydroxyl, on the OH group, we said that in alcohol, well, we saw two of them. They had a pK of around 16 to 18. So let's just scribble that down. pKa equals 16 to 18, doesn't matter. And the last one, when you had a hydrogen attached to a nitrogen on ammonia or an amine, does anybody have that pKa at their disposal? What was it? Around what? 38. Thanks, Hannah. So you have a pKa, which is equal to 38. Now, if you were going, well, come on, Mr. Dion, you're writing, 43 to 44, 16 to 18. Now, is it unequivocal or what? Absolutely. It's unequivocal that this proton, the one in blue, definitely has the lowest pKa, and therefore it is the most acidic. All right, now if you're wondering, what's the relevance of all this? Well, where are we trying to go? What's the purpose of what we're studying right now? We're kind of laying some foundations to get us to the point where we can start looking at reactions. And when you want to look at a reaction, we're going to look at a lot of acid-base chemistry. And so you want to be able to look at a molecule quickly, even a big molecule, and say, well, this is the most acidic proton. This is the one that's going to be involved if there's a strong base or whatever, right? So what you really need to train yourself to do is to be able to look at a molecule, recognize functional groups, acidic protons, basic protons, and all that stuff. So that's kind of what we're doing right now. Let's take a look at another question here. This is question 3.7. It says, identify the stronger base in each of the following cases. There's two questions here. Question A and question B. I'll divide the page in two pieces here. So if I call this one A, and I call, well, maybe I'll use numbers since the problem. Number 1 and number 2. Can anybody tell me which one of these is going to be a stronger base? Well, the way that we're going to do that is we're going to look at the conjugate acid. So if we draw the conjugate acid of this compound, we end up with an alkyne. All right, so we end up with an alkyne here. So that's the conjugate acid. And the conjugate acid of this compound or this ion, could anybody name the conjugate acid of number 2? What's its conjugate acid? If you take NH2 minus and it gains H plus, what do you end up with? Well, not ammonium, ammonia. Right? You'd end up, because you're only gaining one proton, you end up with ammonia. This compound here. There we go. Great. So now what we're going to do is we're going to look at the pKa's of both of those. And the pK of the alkyne was 25, and the pK of ammonia was 38. So which one of these is going to be a weaker acid, right? The one that's the weaker acid is the one with the higher pKa. And so if this one is the weaker acid, it's going to produce the strongest or the stronger base, right? Because the weaker the acid, the stronger the base. Okay, so based off of that, no pun intended, I'm going to give you a second to look at the one on the bottom. See if you can, that's not a very pretty bond. See if you can identify which one is going to be the stronger base. All right, so if we look at the two of these, if I call this one, I'll call this one 3, and I'll call this one 4. Which one is going to be the stronger base? Would it be 3 or 4? Absolutely. It's going to be 3, right? Because 3 is the weaker acid. It has the higher pKa, right? So this one has the higher pKa. This one's 18. This one's only 16. So this one is the weaker acid, and therefore this is going to be the stronger base. There we go. And that's how we can identify which base is stronger or weaker by looking at the pK of the conjugate acid, because you got to remember that the stronger the acid, the weaker the conjugate base, and then the opposite is also true. The weaker the acid, the stronger the conjugate base. All right, fundamentals here. All right, well, let's move on from there. Let's get into using pKa values to predict equilibria. So we have a couple slides in this. It says, with the relevant pKa values, you can predict which direction an acid-base equilibrium is going to favor. The higher pKa is the weaker acid. Well, that's just review. So if we look at this reaction that's shown down here, we have the tert-butoxide ion plus water gives you tert-butanol plus a hydroxide ion. We have water, which has a pKa of 15.7, and then we have tert-butanol here, which has a pKa of 18. Either way, it's an acid and conjugate acid. Which one is the stronger acid, water or the alcohol? Which one is the stronger acid? Right. Thanks, John. This is going to be the stronger acid, and this one is going to be the weaker acid. All right, so let's think about it. I'm going to try to go back with me. All right, so can everybody see me right now? I'm assuming you can. Right here, fix it a little bit. All right, so this, I'm going to try to explain something using my hands. If you have a strong person and a weak person, and they're pushing against each other, right? Imagine my fist is a big strong person and my finger is a little weak person, and they're pushing against each other. Which way is when they're pushing, you know, giving everything they got, which side is it going to end up on? Is it going to end up on the side of the strong person, or is it going to end up on the side of the weak person? It's going to end up on the side of the weak person. So it's the same thing with an acid, right? If you have a strong acid and a weak acid, what's the definition of a strong acid? It's something that donates a proton. So and the weak acid is trying to donate protons too, but the strong acid is going to donate its protons and it's going to push it over to the side of the weak acid. All right, so that is a fundamental that you've got to be aware of. Let me go back to my screen. And the reason I really stopped there with you for a second, and I am recording this, but whatever, it doesn't matter. You know, the first class I ever taught at, in organic chemistry, I actually taught organic chemistry 2. So they started me in organic chemistry 2. And I was just, you know, teaching along one day, and anyhow, I like to ask questions about Organic 1, the class that you're all enrolled in right now. And I said, okay, well, you've got a strong acid and a weak acid. The equilibrium lies to the side of. And the whole class went to stronger acid. I almost fainted. I almost fell down. Like, I was so shocked that my students said that maybe they were just having a bad day or an off day or something like that. But if there's one thing that you remember, I hope you remember everything from today's lecture, but if there's one thing you really want to be sure of today, it's that if you have an equilibrium between a strong acid and a weak acid, the equilibrium is going to lie to the side of the weaker acid. Why? Because the strong acid is going to do its thing. It's going to push everything. It's going to donate protons more than a weak acid, and it's going to push it to the side of the weak acid. Give me a thumbs up if you're with me on that idea. You can see I'm pretty excited about it. Okay, it's such an important concept, and I don't know why. You know, anyhow, I don't know what I'm trying to say, but you know, you really don't want to mix that up, right? As long as you understand an acid is a proton donor, well, the stronger it is, the more protons it's going to donate. Yes, this guy's trying to donate protons too, but it's only like meh, just donate. And this one is like way stronger, right? It's what, 10 to the power of 2.3, so it's more than 100 times stronger. Okay, anyhow, I hope with all my being that you are going to remember this point right here. I don't think I've done this yet to you. This is such an important concept. The equilibrium is going to lie to the side of which acid? The weaker acid. All right, I feel like I've harped enough on that, so I'll move on from there. All right, so if we look at this reaction, if we have a base reacting with water, which is behaving as our acid, somebody drew some beautiful curved arrows here. There's a bond being formed, there's a bond being broken. Okay, then we get our conjugate acid and our conjugate base. Look at the difference in pKa's here. I mean, is this a huge difference in pK or what? Water is a pK of 15.7, and alkane has a pK of 50. Okay, in this case, we draw an irreversible arrow because there's going to be none of the starting materials left over, right? Since the difference in pK is 10 to the power of 34, I mean, that means that for every 10 to the power of 34 molecules of this you have one of these, okay? So essentially none. So in that case, we draw an irreversible arrow. If you're wondering, well, what's the cutoff for when I draw reversible arrows like these and then irreversible? I'd have to double check in the textbook, but I think it's around a difference of 10 pKa units. Usually if it's greater than 10, we just draw the arrow in one direction. And if it's less than 10, we draw an equilibrium arrow. All right, there you go. So you can see that if you were to put, this is called, this would be a butyl carbanion. If you put a butyl carbanion in water, you have no butyl carbanion left over. It just gets converted into this molecule, which is called butane. All righty, there we go. So now what we're going to do is we're going to switch gears and we're going to get into the qualitative perspective. Okay, qualitative. So quantitative was pKa's. We actually memorized the pKa values from the table. We saw the stronger the acid, the weaker the conjugate base, and the opposite was also true. We said if you have an equilibrium between a strong acid and a weak acid, it's going to lie to the side of the weak acid. And now, if you're wondering, well, what do I do if you give me a molecule and it has a proton and I didn't memorize the pKa? Can I still figure out the relative acidities, like which proton is more acidic than another? And the answer is yes. And the way that we do that is we look at the stability of the conjugate base, okay? So remember, what I told you earlier was that the stronger the acid, the more stable its conjugate base, right? If the function of an acid is to donate a proton, it tells you that the stronger the acid is, the more comfortable or the more stable its conjugate base is going to be. So if you're wondering, well, how do I determine the stability of the conjugate base? What you do is you look at the stability of the lone pair. And what that brings us to is a concept developed by the man himself, David Klein, the author of our textbook, and he uses this method that he calls ARIO, okay? ARIO, which he uses to evaluate the stability of a negative charge, okay? So A stands for atom, R stands for resonance, I is induction, and O is orbital. So what I'm going to do now is we're going to take a short break, and then we're going to come back because this is a pretty important section. It's a pretty heavy section, and I think that section 3.3 is also relatively, heavy. So I want to take a short break, and we're going to come back and we're going to go through all of the points of ARIO so that you'll understand it, and then we're going to try a few practice problems with it.